All right, so in this video, we're going to take a look at some of the examples in the solutions module. And in the first one here, we're looking at calculating the molarity using solute moles. And the first thing to remember is that when we're looking at molarity, molarity always means a specific relationship, and that is moles of the solute divided by the liters of the solution. So in order to calculate molarity, you want to make sure that you have the correct units that we want to divide. So it says, in this example, they're making a solution of aluminum sulfite by measuring 120. So we're using here now, write down the numbers. We have 120, and that's micromoles. Okay, so remember that's a metric prefix, micro. Moles of aluminum sulfite. So that's Al2 SO3 three times. Into a 200 ml volumetric flask and filling the flask to the mark with water. So that means the total volume then of the solution is going to be the 200, and in this case, it's milliliters that we're dealing with of the solution. Okay, so you want to look at the question, process the information that's given, and here, specifically now, you're asked to calculate the concentration in millimoles, so M moles. So this is what we need now. We don't need molarity, but instead we need millimoles per liter. Okay, so this M here is small m, metric prefix, that means milli. So what we would need then, in the numerator, we need millimoles of the solute, and we need liters of the solution. Okay, and once we have those, we can just plug it into this relationship, and then we can evaluate the numbers that we have. So really, this just boils down to some conversions. So if we have 120 micromoles of the solute, this is the aluminum sulfide in this case, we want to convert that now to, we want to end up with millimoles of the solute. Okay, so what's the relationship between micro and milli? Well, which is the bigger unit? Well, milli is the bigger unit. For every 1 milli of something, you have 1,000 of that micro of that something. So in this case, we have 1,000 micromoles and every 1 millimole. So we set it up using our dimensional analysis. So the units cancel out. So we end up with 0.120 millimoles of the solute. Okay, so that's the numerator here that we just found. This part. We still need the volume of the solution in liters. We were given the volume in milliliters, so that's another metric conversion. So for every 1 liter, there's 1,000 milliliters. Milliliters goes away. So we end up with 0.200 liters. That's our liters of the solution. So we can now go ahead and divide those two to end up with the concentration units that this is specifically asking for. So we have 0.120 millimoles divided by the volume in liters, 0.200 liters. So evaluate that. So 0.12 divided by 0.120 divided by 0.200. Okay, and that's going to give 0.600. The three significant figures, millimoles per liter. So in questions like these, you're calculating concentrations, and in some cases, it asks you the specific units that you need. So you want to make sure that you convert the quantities given to the correct unit, and then simply divide the moles by the liters or the correct units by each other to get the answer in the appropriate units. All right, so in this one is an extension of the previous question, where now we want to calculate the molarity using the solute mass. Okay, so again now, if we're given, or if we look at the question here, it says that we're given the need to prepare a solution of copper-2 fluoride by measuring out. So we have 0.026 grams of the copper-2 fluoride, the CuF2, into a 450 milliliter flask and filling the flask to the mark with water. Okay, so we're given initially here the mass of the solute, and then we're given at the end the volume of the solution, which in this case is 450 milliliters. Okay, so what do we need to calculate? We need to calculate the concentration in moles per liter. So what we would need to do then is we want to convert the mass of the solute to moles of the solute, and we want to calculate or convert the volume of the solution to the correct unit. In this case, it's liters of the solution. All right, so and then depending on what the question is asking, yours may not say moles per liter. It may say some slightly different units. You want to make sure that you convert it to the correct unit. Similarly, if you're given masses in milligrams or micrograms, you want to make sure that you convert it to grams first before you go ahead and do the mole conversion. So if we are going to convert mass to moles, okay, this conversion here, we're going to use the molar mass, right? Because that's the relationship between mass and moles, in this case, of the copper 2 fluoride. Okay, so if I have 0.026 grams of CuF2, I can now use the molar mass of CuF2. So for every 1 mole of copper 2 fluoride, I add up, and I look this up on the periodic table, 1 copper plus 2 Fs, and that should give me the molar mass, and I'll plug that in underneath in grams so the grams can cancel out. So in this case, that will be 101.54 grams of CuF2. Okay, I just add up 2 fluorines, 1 copper from the periodic table, and I just divide now the 0.026 divided by 101.54, and that's going to give me 0.01256. We'll take one more decimal place. 1 moles of the CuF2. Okay, so that's my numerator that I've just calculated. I also need the denominator in liters, so the volume in this case. Okay, I'm given 450 milliliters of the solution. That's a metric conversion. So for every 1 liter, there's 1,000 mils. So we end up with 0.450 liters as the volume. So now to calculate the concentration in moles per liter, we divide the 0.0002561 moles by the 0.450 liters, and then that should give the concentration in the correct unit, which in this case ends up being 5.7. Let's see, because we have 2 sig figs in our original number with the lowest number of sig figs. All we're doing is multiplying and dividing. So 5.7 times 10 to the negative 4 moles per liter. So questions like these involve applying concepts that we learned before. So for example, converting grams to moles, that's a molar mass conversion. We did that a couple of weeks ago. Metric conversion, milliliters to liters, or any other unit of volume to liters. That's a metric conversion that we've done since the 2nd or 3rd week, maybe the 1st week of the semester. So you want to make sure you get it to the correct unit, and then we just simply divide the solute by the solution to get the appropriate concentration units. All right, so in the next one, we're going to take a look at, we're looking at the concept of dilution. And generally, when you're posed with a problem that is going to involve dilution, you'll either see the word dilute or diluted or dilution in the problem. That's where you want to think about this particular process. And when it comes to dilution, there's an equation that relates what we're doing here. That's the dilution equation, and that's C1V1 equals C2V2. Okay, so if you multiply the initial concentration by the initial volume, whatever number I get there, should equal the product of the final concentration by the final volume. So really, when it comes to using this equation, you kind of have to figure out from the problem what's your C1, what's your V1, what's your C2, and then there's always going to be just one of these that is unknown that you need to solve for. So you have to process the info from the question. So it says this person is diluting 36.8 milliliters of this solution until the concentration falls to 9.00 micromolar. She'll do this by adding distilled water to the solution until it reaches a certain final volume. Calculate this volume in liters. So right away, we're told from the question that we need the final volume. So the final volume here would be V2. So right away, what I can do is I can rearrange this equation and I can solve it for V2, okay? And rearranging this equation or equations like these would be something we've done previously. Actually, in the last module, you looked a lot at gas laws, which involved equations very similar to these, and you had to rearrange them. It's basically algebra that you're doing. So if we rearrange this equation, we solve it for V2, what we find is that V2 is simply equal to C1 times V1 over C2. Okay, so we would need to find these in the question and then substitute them. So what is my initial concentration? The initial concentration is always going to be greater than the final concentration, because when you dilute something, this concentration decreases. So initial concentration here is 36.8 micromolar. And then we're diluting that to the final concentration. So it falls to, so my C2 now is 9.00 micromolar. And that makes sense. You dilute something, the concentration decreases. My initial volume, V1, was 36.8 milliliters. So the same number in the volume and the concentration. And again, my V2 is what my unknown is. So I can substitute these values now into the equation. So I have my C1, 36.8 micromolar. Keep track of your units because they will help you here in the end. V1 is 36.8 milliliters. My C2 is 9.00 micromolar. Okay, and that's going to be equal to V2, whatever that is. Micromolar cancels. I end up now with milliliters as my unit for V2. Well, guess what? The question is asking for the final volume in liters. So you still actually need to do one more thing. So let's evaluate this. I have 36.8 times 36.8. Whatever I get, I'm going to divide that by 9. And that's going to give me 0.015. We'll keep a couple extra decimal places. Well, let's see. We have 1, 2, 3 sig figs, 3 sig figs, 3 sig figs. So this number here should have 3 sig figs. So 0.0150, that would be my mils to get to liters. Okay, that's another metric conversion. So in every liter, there's 1,000 mils. So we divide by 1,000, in other words. So this becomes 0.123, and then 0.150 liters. Obviously, that's a little cumbersome to work with, so we can express it in scientific notation. So we have, let's see here. One sec, let me double check. 36.8 times 36.8. And I divided that by 9. Oh, I'm sorry. Let me double check. This should be, the answer here should be 150.47 milliliters. Okay, so 150.47, we divide by 1,000. This is incorrect. Move the decimal point 3 places, so this would be 0.150 liters would be the final volume. And then we have 3 sig figs in our answer. We had 3 sig figs and everything else. All right, so in this one, we need to identify the correct sketch of a compound in aqueous solution. And it says you need to move the slider across to try to identify which of these would be the best representation of when a solution of this particular compound actually forms. So the first thing that we need to figure out in questions like these is the compound ionic or covalent? Okay, so if it's ionic, it will break into its ions, so it will break apart. And those ions will separate in the solution. If it's covalent, generally, what we're going to assume is that it will stay together. So not break apart. So for instance, if I have carbon monoxide, CO, okay, if ionic or covalent, well, we look at the types of atoms, they're all nonmetals, so this would be covalent. So this will stay as CO molecules in solution. So I have a C and an O connected together. So if we slide across, we're looking for two spheres connected together. Obviously, we have two here, but these are the same. So the C and the O need to be different colors, and they need to be linked together. So if I keep scrolling across, maybe this one could have a C and an O, a C and an O. The background spheres are just water molecules that are the main part of the solution. If I keep scrolling, this one has three, so that's not going to work. So maybe this one then, one C and one O, one C and one O. That would be the best representation of that. If instead we're dealing with something like an ionic compound, like MgCl2, that's magnesium chloride, we can tell that it is ionic because usually once you see a metal in there, we can think ionic. So what are the ions that make up magnesium chloride? All right, so you need to remember now back from the bonding chapter that we have magnesium ions and then we also have chloride ions. Well, according to this formula, we actually have, for every one of these, we have one magnesium, but we have two chlorides. Okay, so I actually get 3 particles for every one MgCl2. So if I slide across, I can see now, well, these are broken up, but are they in the correct ratio? Well, let's see. Keep going, keep going. So probably the only one here that is indicative of what we're seeing would be one where the ions are all separated from each other. All right, so we have the one that we said before, and then this one here, the magnesium ions separated, and then we have the chloride ions that are separated as well. You will notice that they're in the right ratio also. So if the blue is magnesium, we have 2 of the yellows, the chlorides, another blue, and we have 2 of the chlorides that go along with it. So in this one, we're looking at calculating the mass percent composition of a solution. And this is just another way to represent the relative amounts of each of the components. And this is based on the whole idea of percentages in the first place. And remember, a percentage is simply the part over the whole divided by, part over the whole times 100 to turn it into a percentage. So in each of these questions you're given the amount of each of the components. So the whole here is simply the sum of everything. So we have 31 grams of the chloroform. We have 85 grams of the heptane. We have 96 grams of the acetylbromide. So we put those together. So 31 plus 85 plus 96. Try that again, 31 plus 85 plus 96. So that is going to give me 212 grams. Okay, that's the whole. And then the part now is for each of these. So the percent chloroform is simply the mass of the chloroform over the mass of the whole thing, the mixture, And then as a percentage, we just times it by 100. So in this case, the chloroform is 31 grams divided by 212 times 100. And then that's going to give us whatever value. In this case, we have to have 2 sig figs in each of our answers. So you do that for each of the components of this mixture or this solution. All right, so then the last one here, we're looking at applying a very important rule when it comes to solutions. So the whole like dissolves like is a very simple rule, but it's a rule that we can apply to lots of situations, not just chemistry, but in biology as well. So essentially what this rule says is that in order for a solute and a solvent to mix well with each other, they have to have similar polarities. So there must be like or similar polarities between the solute and the solvent for a solution to form. Okay, so both the solute and the solvent must be polar, for example. It must both be polar, or the solute and the solvent must both be non-polar. So like dissolves like, similar polarities between the two components. So really in each of these cases, what you need to do is to figure out, well, is the solute polar or non-polar? Well, in this first example here, I have I2, which is made up of 2 I's, right? You have 2 things connected together. That is obviously going to be a non-polar molecule. Electronegativities are identical. Even sharing of electrons, non-polar bond, non-polar molecule. So in order for this to form a solution, it would prefer to mix with a non-polar solvent. Okay, one thing to keep in mind is that water is very polar. Okay, so right away we can, by process of elimination, select the second one, which is made up only of carbons and H's. So whenever you see structures that have lots of C's and H's in them, we can assume that those are going to be non-polar molecules because all you have are carbon-hydrogen bonds. Okay, those are non-polar bonds. So in the second one here, if you look at the structure, you'll see, yes, there's a bunch of C's and H's, but you also have these OH's, all right? And whenever you see OH's, those are very polar bonds. If you have lots of them, that will lead to the molecule being polar as well. So in this case, we can assume that this is going to be fairly polar. We want to select which of these options is going to be more polar than the other. So if you look here in this CH3OH, there's an OH, which would make this a fairly polar molecule. In the second one, it's a lot bigger, and there's a lot more C's and H's in this than there is in the first. So we can assume that that one is going to be more polar. And you just continue that process all the way through. You identify the polarity of your solutes, and then the better solvent is going to be the one that has a similar polarity associated with it.